So, okay. So thank you for the introduction. Actually, this is the first time I joined this IoA seminar. So, so I'm Terry. I'm currently the third year PhD student in Professor Goto's group. So first of all, I want to thank all of the collaborators, including my supervisor, Dr. Yamamura and Nakagawa from Japan Aerospace Exploration Agency, and other co-authors from NTHU, NCHU, and ANU. So today I'm going to talk about Planet 9. So when you hear about Planet 9, then you may have a rough idea about the 9 planets in our solar system, right? But I'm not going to talk about Pluto, which was reclassified as a dwarf planet in 2006 because it's low mass, and which is only 0.2% of the Earth mass. Then it's very small to have a strong impact on the object in the outer solar system. So here I'm talk about the hypothetical planet in the outer solar system. So first of all, we'll talk about how people come up with the idea about Planet 9. So let's go back to more than 10 years ago, since the discovery of Sedna and Sedna-like object. When scientists analyzed the orbit of this Kuiper object, they found that these objects showed very unusual orbital clustering, not only in argument of perihelion, but also in the physical space. So this is very weird, right? So imagine a real situation when you go to Taipei main station, everyone walk on the same way and looking at the same direction. This is almost impossible unless someone or something forced them to do that. Then we apply the same logic here. This orbital clustering cannot happen randomly due to chance unless it's related to an unknown dynamical mechanism. So in 2016, simulation work done by Patigan and Brown, they suggest that the probability for this orbital clustering can happen randomly due to chance is only 0.007%, which almost impossible. And they also suggest that a giant distant planet with at least 10 Earth mass and the orbital semi-major axis of 700 AU can maintain this orbital clustering, and they call it Planet 9. So this is how they come up with the Planet 9 hypothesis. So here is the simulation from Patigan et al. 2016. So before playing this video, the pink one here is the possible orbit of Planet 9, and the blue one is the blue orbit, the orbit of the high elongated Kuiper belt object, and the green one are the orbit of more shorter orbital period object, but which are not the member of orbital clustering. So at the beginning, you can see some of the blue orbit located collinear with the orbit of Planet 9. But after the evolution, the long-term evolution of 2 billion years, they scatter away to the opposite side of Planet 9 orbit, and only these blue orbit can survive, and they cluster together like we observe nowadays. So if Planet 9 can be confirmed in the near future, this would be a strong impact discovery because we need to rewrite the history of the entire solar system, and it will change our understanding about the dynamical structure of our solar system in the early stage. So indeed, since the discovery of Neptune in 1846, we don't have any planet. Our solar system still remains with 8 planets. And what if we have another planet far beyond the Neptune orbit. And so if Planet 9 can be confirmed, people may want to ask other questions like, could Planet 9 be formed at the beginning in the inner solar system and then later got ejected by the gravitational interference of other giant planet, or it's just a free-floating planet that captured by our sun? That we don't know. We need to find the answers for this question. But the most important task is to identify the existence of Planet 9 by observation. So actually, in the past, many groups searched for Planet 9 using optical surveys, like using ZTF, Dark Energy Survey, or PS1. But turns out they only constrain the possible orbital parameter for Planet 9 without successfully constrain any good Planet 9 candidate. So the question is, are there any challenge in finding Planet 9 using optical survey? The answer is yes, because the Planet 9 is very far away beyond the Neptune. So the sunlight need to travel twice from the sun to Planet 9 and then reflect back to the Earth. Then the reflected sunlight degenerate very fast. Compared to the thermal emission from Planet 9, only need to travel once. So the infrared surveys will be way better than the optical surveys. And on the other hand, the light will be absorbed by the Earth's atmosphere. So it's better to have the space telescope rather than the ground-based telescope. So another thing is the location of Planet 9 is uncertain. We don't have any well constraint on the orbital parameter and the mass of Planet 9. So we don't know where it is on its orbit. So that's why we need the all-sky surveys. And among the infrared all-sky surveys, the infrared astronomical satellite and Arcturus space telescope, they did the all-sky surveys in the infrared wavelength, and they meet the requirement for the infrared filter. So previously, there are two groups also searched for Planet 9. The first group, led by Rowan Robinson in 2021, he used IRAS, only IRAS, to search for Planet 9, and Sedgwick and Surgeon in 2022, they used the combination of IRAS and Arcturus, but the Arcturus data they use is just the Arcturus bright source catalog, and actually they found 500 candidates, but all of them located near the galactic plane, which is significantly affect to the flux measurement. So actually they don't propose any good candidate. Okay. So in this research, we, in addition to IRAS datasets, we use Arcturus survey. So, but in the Arcturus bright source catalog, the moving source are not included. So this is not ideal dataset for Planet 9 search. Instead, we use another dedicated source list for Planet 9, which is called Arcturus monthly unconfirmed source list. They include a moving source that has no monthly confirmation, and this is very good for Planet 9 search. So the basic difference between these two datasets is the definition about the real detection. So for Arcturus source, bright source catalog, they require about 75% of the scan, of the total number of scan detection. But for Arcturus MUSL, they only need 2 detection, no matter how many scans pass by that object. So the condition is more relaxed. So that's why we have more moving source. And again, thanks to Dr. Yamamura and Nakagawa from JAXA for working on and providing us this data set. They and my professor are the member of Arcturus mission, so this is another advantage for our group. So the epoch difference between IRAS and Akari are 23 years, which is large enough to detect the slow motion of Planet 9, which is just a few arc-minutes per year. And we expect that Planet 9 first detected in IRAS in 1983, and then 23 years later, it will move to another Akari position in 2006. So, first of all, we want to search for Planet 9, and we need to estimate the expected orbital motion. So, in the long time scale, the orbital motion will be dominated over the parallax motion, which only dominates with shorter time scale, like several months. So here we adopted the formula from Cowan paper in 2016. They estimate the orbital motion of Planet 9 per day at a distance of 700 AU, and we just rewrite this formula for our case, which is 23 years, and we have the equation 2. So here's the relation between orbital motion and the heliocentric distance of Planet 9. So if you go shorter distance, the orbital motion will be increased like this. So next, we want to estimate the blackbody radiation by assuming that Planet 9 have a temperature of 50 Kelvin. This is from Cowan et al. 2016, and you can see the blackbody peak is at about 100 micrometer. And then here we search for Planet 9 from 7 to 17 Earth mass, and within the distance range of 500 to 700 AU. You can see here, if Planet 9 have 17 Earth mass, then the expected flux will touch the detection limit of IRAS at 700 AU. So this is the upper limit of our searching range. We cannot go further, otherwise it will be below the detection limit of one of the two surveys. Okay, so the basic idea is to narrow down the number of IRAS and Akari, which is more than 2.3 million sources in total. And we need to remove the stationary and too bright sources, which is unrealistic to be a planet. And then we exclude the galactic plane and galactic bulge region, because these two regions significant affect to the flux measurement. So that's why we need to exclude them. And then we make a list of the single IRAS or Akari detection, because here we use the combination of two surveys. Then we need to prepare the single IRAS or single Akari detection. Then we will make the pair based on the angular separation of the IRAS and Akari over 23 years. Okay, so the general idea is we search for moving object from IRAS to Akari. Then we need to make sure that all of these objects have flux above the detection limit of IRAS or Akari. Then we create a candidate pairs, including one IRAS source and one Akari source, based on the angular separation. So here is 42 arc-minutes to 70 arc-minutes. This corresponding to the distance range of 500 to 700 AU. Okay, so before the visual image inspection, we have 13 candidate pairs, and then we check each of them, and then actually we found one promising candidate. So this candidate first detected in IRAS image on the left, and then after 23 years, it disappeared from the same position in Akari image. And then we expect that if we move to Akari position here, so you may wonder why you don't see any detection at the location of Akari. This is because this Akari image is for Akari bright source catalog. And as I mentioned before, the definition of the real detection of Akari bright source catalog is more strict than the Akari MUSL. So in reality, we may not see the real detection here, and we have to use another solution, which is the Akari detection probability maps. Then we see the detection here. Then this is just one scan in that map. Then I will show you the full Akari detection probability maps. So in the lower rows, you can see there are 2 detections on the same day, but different hours. And 6 months before, there's no detection. So this is consistent with the slow motion of Planet 9. So this is one of the bad candidates. So here's the Akari image. So after 23 years, the IRAS source still here. It still appear very bright here. And also, this image was contaminated by the cirrus region, which is not good. And another bad candidate is, actually this candidate can pass the previous step, which is the visual image inspection for IRAS and Akari. But here, there are 4 scans here on the same day, but only 2 of them have detection and other 2 are non-detection. So this could be a fast-moving object. So to estimate the mass and the distance of our candidate is quite simple. So we already know the angular separation between IRAS and Akari, which is 47.5, and then we can trace back the distance, which is 645 AU. And when we know the distance, we can plot the relation. And also we know the flux at 90 micron. We can plot the relation between mass and the distance. Then we know that the mass is about 11 Earth mass. Okay, so this work was already published in PASA in May 2025. And then in this paper, we found one good candidate between 500 to 700 AU. And when I checked the latest status of this paper, it's got the attention score more than 1,000, which is the huge motivation for us. This is because our paper was featured on the news outlets like Science Magazine, Astronomy Magazine, and so on. So I think this is a good way to promote our research to both astronomers and non-astronomers. Okay, so what's next after this paper? So because IRAS detection and Akari detection alone cannot determine the full orbit of our candidate, so that's why we need more follow-up observation to determine the Keplerian motion of this candidate. Then here we can propose the Subaru HSC or dark energy camera. It depends on where Planet 9 candidate is. So in my case, my candidate located in the southern hemisphere, so the dark energy camera will be better. But if we search for the closer distant range, we may find more candidates in the northern hemisphere. Okay. And in summary, we take advantage of infrared survey over the optical survey to search for Planet 9, and we propose one promising candidate within 500 to 700 AU. And then we need more follow-up observation to determine the Keplerian motion of Planet 9 candidate. And in the near future, we'll complete the full distance range based on the simulation result, which is 280 to 500 AU. So at this distance range, the angular separation will be increased significantly. Then, of course, we'll invite more candidates. And to check the image of IRAS and Akari is time-consuming and manpower-consuming. So I think in this case, machine learning will be a good approach to classify the candidate. So I think that's all for my talk today, and I'll stop here and take your questions. Thank you very much.
We have a very nice question.
Yes.
What about the trajectory of this planet line? Like, will it follow like the other planets in the solar system, like with the Newtonian mechanics we know so far, or?
Yeah. So actually, I make this plot, but the estimation for the planet 9 orbit is only based on 2 detection. So it may not very precise, but it can give you a brief idea where you can search using the follow-up observation. Yes, you can estimate where it is based on the epoch between Akari and another survey. Yes, and I make this plot compare with other noise that noise. Yes.
Any more questions?
Yes.
Did you say that you plan to use future surveys to look for more candidates?
To identify this candidate in this paper, and also if we search for closer distance range and we found more candidates, then we also use the follow-up surveys to identify other candidates. Yes.
Right. So if you, in the future, you find more candidates, how would you confirm which one is more likely to be planet?
Yes, that's the good question, because in the shorter distance range, we'll invite more candidates, and to identify which is very difficult. Because one IRAS source can match with a lot of Akari source, and we have to identify which one is the true counterpart. And one thing I didn't include in my paper is the inclination of the orbit and other orbital parameter. In my paper, we only have like distance and mass. We don't have other orbital parameter. Then I think if we apply the criteria for that orbital parameter, then we can limit the number of candidates. Yes. Thank you. Yes.
So going back to your clustering of senoids.
Yeah, the first one, right?
Yeah. So do you know the other reasons? Are there any other reasons for the clustering that you see? Next slide. I think.
This one.
Yes.
So what is your question?
So you see clustering of senoids, right?
Yes.
Do you know the other arguments why there's clustering of senoids?
So I think in another paper, they discuss about the observational bias, but the probability is low, just 0.2%. So actually, the weird thing is they only cluster in one side and nothing in the other side. But I think at that time, they only have a few data of a few set nodes. So later, I think other group found more set node object, and actually one of them are the outlier of the orbital clustering, and it may challenge to the planet 9 hypothesis. Yes. Yes.
The other question is, do you know what is the problem with forming Neptune? At the moment, we have problem explaining the formation of Neptune. Do you know what it is?
I haven't checked this part. Yeah. Yeah. Okay, Abhi.
So you can only find 2 points, right?
Yeah,
one
only
from
2
Sky,
points.
One from Alex.
Yes.
So no matter what, you won't be able to find out the inclination or
So based on these two detections, we can roughly estimate the inclination. Then later when we conduct the follow-up observation, then we can compare, like we combine 3 or 4 points, and then we compare with the inclination. The new inclination value is consistent with the previous one. Yeah.
Previous one, in the sense that
I mean, the previous one, we only have 2 detections, right?
Yeah.
And we calculate the inclination. And then later, if we have more detection,
how can you connect it with 2 points? It can be like up or side or anywhere. You need 3 points for a plane to form. But with 2 points, it's like a straight line.
it just gives you the brief idea, I think the inclination you still can estimate, but for the eccentricity, you cannot. Yeah, and also the perihelion distance. Yes.
If not, let's thank Terry again.
Thank you. Thank you all.